simulator tools. Did you all install the tools? I already shared the recorded session to install.
Hi ma'am, this is Madhav. My installation is still pending. Facing some issue with my laptop, so I want to fix it by tonight.
Okay, no problem. What about Suma? Did you try with the other version?
Yes, with 17 I got.
You got okay. So remaining all, try to install 17th version for model simulator. Okay, Quartus Prime anyway will work with the I think new updated version. But for model simulator, we are facing some errors. Okay, so for model simulator, you can install 17 version. Okay. And what about Ritesh? I think you already have the tool, right? So you can install for SystemVerilog and UVM later on. Remaining all, Lahari, you want to use in web, so you can browse.
I will use EDA tools.
EDA playground. I already told, right? How to use the EDA playground. Okay.
Yeah.
What about others? Any doubts till now? Okay. Okay, fine. So today we are going to discuss on we already discussed the levels of abstraction. Okay, is the screen visible? PPT?
Yes, ma'am.
Yes.
Okay. So what is the difference between behavioral modeling, data flow, gate level, and switch level? So, however, in digital electronics, we will follow some flow, right, to design a gate level circuit. First of all, any problem, whatever the problem statement is given, first of all, we need to understand the functionality of the problem statement. After understanding the functionality, next step is what are the inputs, what are the outputs, and what are the control signals. We need to understand that and just draw the block diagram based on the functionality, what are the number of inputs and how many control signals are there. That means the clock or reset signal or any dependent signals all comes under control signals. And how many number of outputs are there. Some circuits will have single output and some circuits like a multiplexer or demultiplexers have multiple outputs, right? So you need to draw a block level diagram with the number of inputs, outputs, and you need to understand the functionality. Based on the functionality, you need to draw the truth table. So based on the number of input combinations and what are the control signals and what are the outputs, based on that, first step is to draw the truth table. Okay. So once you draw the truth table, you will get the behavior of the any circuit. Okay, so suppose example you have taken a ripple carry adder. Okay, for ripple carry adder, first of all you need to draw the truth table. How many number of input combinations will be there, multiple input combinations, and what are the outputs, the selection outputs or sum and the carry, right? So based on that, you need to draw the truth table. After drawing the truth table, you will be getting the output expression, right? You already know POS and SOP format. Okay, so we can write the output expression from the outputs of truth table using the Boolean algebra or K-map. You can do the minimization of the expression and you will be getting the final expression. So that is what step 2, getting the expression in the digital logic design. What is the step 3? From the output expression, we need to draw the gate level circuit diagram. Okay, so whatever the diagram we draw in terms of gates, there will be some AND gates, NAND gates, NOR gates, or any OR, XOR, XNOR. By using these gates, we will draw a basic circuit diagram. Okay, gate level netlist. From the gate level netlist, if you want to draw CMOS level, that's what we call as a transistor level, because the main technology in fabrication, we use a CMOS technology. Then beyond CMOS, we have used a lot of technologies like FinFET, GAAFET, MACFET. There are a lot of nanosheet technologies out there, but mostly in every curriculum, like in your course curriculum or a BTech level or master level, we will learn the CMOS designs only. So mostly we will focus on CMOS design. Okay, so these gates can be converted into the CMOS circuit. You can draw the CMOS netlist. Still, if you want to further convert to some stick diagrams from CMOS level to stick diagram, actually that is a backend part. Okay, so in the backend part, from RTL to GDS level, we do the stick level diagrams and all. Okay, but as of now for DB, it's not required. Okay, for doing synthesis, up to gate level netlist is enough. We don't consider the even transistor level, CMOS transistor level. Why? Because if you want to write a program for some functionality, here I'm just explaining as a ripple carry adder, full adder, multiplexer, like that. But in real time, we design the architectures, right? I already shown you, right? This SOC design structure, where the SOC consists of some processor, ALU, register, counters, lot of blocks involved in a single SOC, right? So if you want to design one by one, we will design each block separately and we will connect a whole in top level. Okay, so if you want to design separate block, if you write a more complex code, it takes a lot of time, right? If you write in a transistor level, because in a SOC, it consists of nearly billions of transistors. Okay, is it possible to write a program in billions of transistors? Is it possible? Hello. Is it possible to write a program in billions of transistors?
No.
It's not possible, right? Even we cannot design a architecture for those transistors. Okay, those are automatically generated in the backend process. Okay, so in the front end, mostly we will focus on behavioral modeling, because behavioral modeling is a just logical, just a functionality we can put in the coding wise. Okay, we don't need any gate level circuit. We don't need to draw a number of gates, lakhs of gates. We don't need to draw, just a functionality we can put. And data flow also mostly considerable, because by using the expression, sometimes both behavioral modeling and data flow modeling, we both combine. Okay, so once you look into the programs, programming style and all, you will get understand. Okay, so writing a program is not a matter. Anyone will write the program, but how logically we optimize the code, within a single line program, sometimes how logically we implement the complex programming, how we can write in a simple style. So that is very important thing. We need to focus mostly on those. Okay. So after this session, I am going to share a Verilog assignment to you. You no need to try directly on the tool, but try to write on a book. Okay, so if you, because this is a first assignment, the first session, right? Practically, so no need to put everything on the tool as of now. Just try to understand the problem statement. There are nearly 30 problem statements will be there from starting onwards, from basic onwards. So try to understand and try to write down with a pen. Okay, no need to implement in the tool. So after in the by next session, you can write the program on the tool. Okay. So first of all, we are going to write the program using a behavioral model. Behavioral model is nothing but whatever before I said, truth table. By using the truth table, if we write the program, that's what we call as a behavioral. If you write the program using output expression, that's what we call as a data flow. If you write the program using the gate level structure, that's what we call as a gate level modeling. If you write the program by using the CMOS transistors, we can call it as a switch level modeling. Okay, in Verilog we have a 4 levels of Verilog programs. Okay, in these 4, which is mostly considerable in industries practically to design a projects in the sense, first priority is for behavioral modeling, second priority is for data flow modeling. Gate level we can use, but like third priority. Okay, first is a behavioral, because in behavioral we can design any functionality in easily. Okay, we can write a logical way, just like a C language. In C language, how we will write the lot of designs like programs, Armstrong numbers, or even odd programming. We don't have those type of things here, but it is somewhat similar to the C language. We use a loops, if else program, case statements we use. So it's similar. Okay. Next. So first of all, to write any program, there will be a syntax, right? How many of you have idea on Verilog HDL? All you all freshers, or do you have any idea on Verilog? Hello. What about Madhav, Ritesh, Rehab, Lahari, Tranita?
Just a brief idea we have on the syntax, ma'am.
Okay, only on syntax. You just know about the syntax, not in depth of
Yes.
coding.
Yes.
Okay, fine. Okay, see. So first of all, to write a Verilog program, we need to follow some syntax. Okay, so like C language or whatever the programming style, we have some syntax, right? Same here also. So whatever the Verilog program, whether it is a design or a test bench. Okay, we have two things. One is for synthesis, one is for simulation. Synthesis is nothing but design, writing the program, and if you put the program into the synthesis tool, we will get the circuit netlist. That process we call as a synthesis. If you do the verification, that means if you apply the test bench to the design, that process is called simulation, verifying the output. Okay, we already installed both tools. One is for synthesis, one is for simulation, right? So now we'll see what is the syntax. Okay, so first of all, module, end module. Okay, so in Verilog HDL, whatever the program we are writing, whether it is a test bench, behavioral, or data flow, or gate level, or switch level, whatever, we should write within the module, end module. Okay, so after the module, it is a module name of the module. So it is a user defined. Okay, suppose if you are writing for full adder, then you can put as a full adder. If you are writing for multiplexer, then you can put as a mux. According to your particular project, you can give your own names. Okay, next, port name. Here the port list. Port list in the sense, every design there will be the ports, input port and output ports. Suppose there is a hierarchical multiplexer. Okay, hierarchical multiplexer means here there will be one multiplexer, and here there will be one multiplexer, and here there will be another multiplexer, suppose. Okay, so inputs are A, B, and main output is out. Okay, and this output is sending to here, and this output is sending to here. Okay, these are like here C is the output of first multiplexer, here D is the output of second multiplexer, here is the main output. Okay, so now here what are the ports? What are the ports? Ports in the sense, only A and B are the input ports, and out is the output ports. These are the main three ports. Okay, but whatever their middle, these are interconnections. That means output of one gate is sending to the input to the another gate. Here also output of one gate is sending to the input of the another gate. So these are not considerable as a port. Okay, so whatever the main input and outputs are there, those are considered as a ports. So you need to mention here what are the ports, like A comma B comma out. These three are ports. Remaining C, D are just interconnections, just like a wire connections. Okay, so here this is one wire connection, another one is wire connection. That's why C and D we will declare as a wires. Okay, so after that, declaration of port and data type. Okay, so here we just given A, B, C, A, B out, but the internal system doesn't know whether A is a input or B is a input or out is a output. Maybe it may consider out as a input and B as a output. It will be happen in that way. Okay, so for that purpose, the ports must be declared. What is the input and what is the output? Okay. So here for at port declaration, we need to write as input A comma B, output out. That is the port declaration. And data type declaration. In Verilog HDL, we will have the data types. In C language, however, we have integer data type or float data type, some string data type. There are multiple data types, right? So in Verilog HDL also, we have a synthesizable and non-synthesizable data types. In the next session, we will discuss about the data types. Okay, just a very simple data type. Wire data type and register data type we have. Okay, net and register. So very simple. We will see in the next session. Next thing is task and function declaration. So whatever the functionality. So multiplexer have some functionality, full adder have some functionality, registers have some functionality, memory have some functionality. So whatever the functionality, we need to write inside here after port declaration. Okay. Next, timing specification. Timing specification is means what? In digital electronics, everything will be changed with respect to the time only, right? With respect to the clock signal for sequential logic circuit. For combinational logic circuit, it doesn't have the clock, but outputs will be changed with respect to the time only. Some outputs will change at the 0 simulation time, after 5 simulation time, after 20 simulation time. Like that, outputs will be changing and inputs also will be changed, right? So that's why timing specification mostly we will write in the test benches only. In the design, we don't declare the time. Okay. Next, N module. So within the module, after writing the ports, data types, the timing, everything, then we will write the N module. Okay. So we need to put entire program within the module, N module. That is syntax. Everyone understood here?
Yes.
What about others?
Ma'am, I have a doubt.
Okay.
Can we declare ports inside the section of port name, like after
Yeah, we
module?
can declare here also. Here directly, if you want to declare input A, input B, output out. If you want to declare there, we can. No problem.
Okay. Okay. Thank you.
Any other doubts?
Ma'am, what will we write in the place of module?
In place of module, we write only module. Module and module is fixed for all.
Okay. Okay.
Okay. Other doubts? Any doubts?
How to specify the timing specifications?
Like
Any
hash,
syntax for that?
like hash 5 time units, hash 5, hash 10, like that.
Means it is a delay of 10 seconds or
10 seconds, 10 units. If you want
10.
to mention in terms of seconds, nanoseconds, picoseconds, we need to write a time precision. At globally, we need to mention the time precision so that according to that, it will calculate whether you want to make it in nanosecond or picosecond like that. But normally, we will mention as a hash 5, hash 10 like that. Just it will consider as a units.
Okay.
Yeah. Today we will work on a synthesis. Tomorrow we'll write the test case and I will show you how the waveforms and how we can open the waveforms, how to do the simulation. Okay. Others? Any doubts? Okay. So example of full adder using Verilog HDL. Can anyone explain the code here? First of all, which model it is? Which description style?
Gate level modeling.
Gate
ma'am.
level.
Gate level modeling. Okay. So here, if you observe XOR and 3 AND gates are there, one OR gate is there. So those are gate primitives. Gate primitives in the sense not user defined. By default, those are fixed. XOR, AND, or any gate, NAND, NOR, whatever. Those all are predefined primitives. Okay. So module end module. So within the module end module, we need to write any functionality we need to write within that only. Okay. So it's a full adder. So name of the module is adder. Every time you need to start with the alphabet only. Okay. So if you start any module name with a number or special character, it throw an error. Okay. So that's why every time you need to write a module name with the alphabet only starting. At ending you can mention any number or special character, whatever. Okay. Next, carry sum a comma b comma c. Next, output carry comma sum and input a b c. Like that we need to declare what are the input, what are the outputs. Next, wire w0, w1, w2. I already shown you, right? One gate to another gate, the connections we call it as a wires. Okay, because those are not either input or output. Okay. So first XOR name is U0. Sum is the output. So here first we declared outputs. Okay, then inputs. So whatever the declaration is there here, in the same format you need to write here. So first output, then inputs. Or else if you put inputs first, then last outputs, then also you need to put inputs first here, then output last. That your wish. Okay, we can use any format, both are correct. So XOR sum output ABC or the input. So it will generate one XOR gate like this. A, B, C. Name of the XOR is U0. Output is sum. Okay. Next another AND gate. Name of the AND gate is U1. W0 is the wire. A, B or the inputs. So A, B are the inputs, and here W0, and next one B, C are the inputs, and W1 is the output. Next B, A, B, C, C, A, right? C, A are the inputs, W2 is the output. Finally, OR gate. For OR gate, what are the inputs? Output is the carry. OR gate. Output is the carry. Inputs are W0, W1, W2. So here W0, W1, W2 are wire connections. Okay, not neither input or output. So these all are wire connections. That's why we declare as a wire here. Wire is a data type, and also for combinational logic circuit we use as a connection because it doesn't store any data. We have two type of data types. One is a wire, one is a reg data type, registered data type. Registered means it stores data. Mostly for sequential logic circuits, to declare the outputs, we use a reg data type. For combinational logic circuits, we use wire data type. Okay. So we have a lot of rules for that. We will discuss all the rules. Is it clear till here, everyone? I think this one I already did the synthesis, and last session I already shown you. But once again, we will do the synthesis. So if you install the Quartus Prime, after downloading, after installing, it will look like this. Okay. So you just need to click on New Project Wizard here and click on Next. Here you can give the project name. Okay, so full adder, suppose. Next, you can select either empty project or project template. If you select project template, it will give you the default template, that means syntax end module, module, end module, and input port list. Like that, it just give the small snippet. So you can create using that, but I'm creating empty project here. And also fladder name. Next, and before if you create the template, it will ask how many number of input, how many number of output. So the list it will be given here, what are the input, what are the output, but I have to take an empty file, right? So just finish. Did you all know how to do the synthesis in your tools? Some of you have Xilinx tool, I think. Hello. What about Lahari? Okay, sorry, not Lahari. Ritesh and Rahman, Madhumita.
Ma'am, I have done in EDA, ma'am, EDA playground.
Okay, why?
I mean, earlier, from the beginning, I was doing an EDA playground. That's it. I have not yet downloaded the tool.
Okay, fine, no problem. Actually, EDA playground is a best, but as you are a student level, you need to prefer tool only. Fine, no problem. Okay, same just program I just copied here. Module and what are the input, outputs, XOR and. Okay, you can do save option here. Okay, so I just created directly, but you can create with the name. So Verilog 1 and save. Here run options are there. Run 1, run 2, run 3. So you can use any one option. So do the run. So here you can observe the compilation is successful or not. If you write any error, suppose in place of input, I'm writing some name B1 or something I change here. I didn't keep the semicolon. So first it will do the compilation report is clear or not. Once compilation is free, then it will go to the actual functionality. Okay, that means inside the functionality do run, we call it as an actual test run. Okay, first it do the compilation clear. Compilation clear means the syntaxes, just the syntaxes. Once it check the syntaxes, automatically we will get the compilation free and we'll get the result also. If we get the result, we cannot say it's a final because the functionality may be wrong. So synthesis tool doesn't check with the functionality. Okay, it only checks the syntax error, and whatever the circuit we are writing here, the program, the connections, whatever the connections we are making here, it just give the netlist for that. Okay, so internal functionality, that means whether a plus b plus c is equal to sum, is that correct or not, whether carry value is correct or not, how we can check that thing is through the simulation. Okay, by writing the test benches. So test benches is nothing but applying the test inputs to the design. Okay, so that's what we call simulation. Whatever we are doing now, that is what synthesis. Okay, so what are the errors? If you see Verilog 1, that is the file name. 12th line. 12th line means near end module semicolon. See here, near semicolon is missing and it's unsuccessful. Number of proper. Okay, here it is over detecting the properties and the syntax is missing. Okay, I mean semicolon is missing. Okay, so I just corrected that, and we will get lot of errors once we do one by one programming. We will get the lot of errors, so we will do debugging at the same time. Okay. So compilation is free. After the left side, if you observe here, there are a lot of options, analysis and synthesis. Our main thing is we need to do only synthesis. Next, filter, placement, routing. These are not our things. Okay. In backend of PD flow, we do placement, routing, and clock tree analysis. Here, timing analysis, netlist viewer. Everything is a backend process. Okay. If you install the tools, you can check once. I will show you once here. Go to the analysis and synthesis. We need to check the synthesize in netlist. So go to analysis and synthesis and go to the view report, and also in analysis and synthesis you will find the netlist viewer. Okay, so as we are doing the synthesis, we need to check for netlist only. We can call it as a netlist or circuit diagram, output circuit diagram. Okay, so RTL viewer. It is a RTL design. For combinational logic circuit, mostly we'll get the RTL only. If you're writing the state machine, you can check with the state machine viewer, and also technology map viewer. Technology map viewer in the sense what type of technology we are using here, CMOS technology or FinFET technology, and even logic cells also it will provide. Okay, the combinational. So if you see here the circuit diagram, this is what the program we have written, right? And the names also whatever we have given, U1, U2, U3, U4, U0. U0 is the XOR gate, U1, U2, U3 are the AND gates, and U4 is the OR gate, some carry. Like that, whatever the program you are doing, you can do the synthesis in a same way. So this is what the process synthesis we call. Okay, simulation in the sense we need to apply the inputs A, B, C. A, B, C means how many combinations we will get. Input combinations.
8.
Over 3.
8 combinations. So 0, 0, 0, 0, 0, 1, like that. For 8 combinations we need to check by writing the test bench. Okay, so we will write the test bench. We will write now only. After that, we will see 4 levels of abstraction of multiplexer. Okay, so for test bench, I use mostly EDA playground. I already told you to install the model simulator, right? At the end of the session, I will show you how to use the model simulator. Okay. So you can write the program in model sim. You can write the design and the test bench. If you don't write the test bench, you can do simulation with the design itself. That means directly we need to provide the inputs in the waveform itself. If you write the test bench, we no need to provide the input. No need to change always in the waveforms. Directly it reconnect to the test bench. Okay. So if anyone want to use EDA playground, Lahari, you can go through the edaplayground.com, and the left side I already told you, right? You can select all deck tool. If you have any office mail ID or student mail ID, you can use Cadence, Siemens and Synopsys also. Okay, So I'm using all day. Any tool I can use, I have access for all. So full adder. Okay, this is one type of full adder circuit. We will write for same whatever we have generated now. So same, just copying the design right side, you can copy, and left side we will write the test bench. Okay, so how to write the test bench we will see now. So test bench also we need to write within the module end module. Okay, so after writing module end module, here you need to give the name of the test bench. As we are given the adder for the design, test bench name you can take any name like a TB. I just consider as a TB semicolon. Okay, for design we kept the port list. Okay, but for test bench no need to put the port list, just you can put the semicolon, or you can also put brackets and semicolon. Okay, anything is fine. Now here you need to declare input and outputs. Okay, so inputs we will declare as a wire data type. Sorry, inputs we will declare as a reg data type. Can you tell me why? Anyone have idea?
Maybe because we will have byte information or word information will have more data. So we'll give as input for that. So we will consider it as register.
Okay. Why output should be declared as a wire data type? Even in registers, counters, or sequential logic circuits also we follow same. Outputs must be declared with a wire. In test bench, inputs must be declared as a reg. Why?
Maybe we need to store the input. So in our flow, whenever we call our input variable, so it can remember. So we are using register to store it. Is that correct, ma'am?
How many of you have idea on procedural assignment statement and continuous assignment statement? No? Fine, no problem. If you have idea on that, you will get understand this, but no problem. In the coming session, we will discuss that thing. Okay. As of now, just remember why we use reg for input and why we use wire data type for output declaration. In the coming session, I will ask same question. Okay. Next, we need to connect our design to the test bench. Okay, because in your files, in your server or network, there will be lot of files. Even if you use the tool, model simulator tool, in model simulator, all the files you will having at once. I will show. Actually, I also need to install 17th version. In model simulator, we need to do simulation here, start simulation, and you will get the work area. In work area, you will be having all the files. Okay, so okay, for me work is not getting. Okay, no problem. Tomorrow I will share show you in model simulator. I will install today and I will show you. So we will get a number of files. Okay, so in that files, in hundreds of files, the design and test bench that doesn't understand which design is targeting to the which test bench inputs. Okay, so that's why we need to make the interconnection here. In SystemVerilog, we call as an interface. Same here also we need to do the interface. But in SystemVerilog, we have the complex program which is connected dynamically. But here it is a very simple, just one line interconnection. Okay. So how we will write the interconnection in the sense? First, you need to write the design name. Okay. Adder name. DUT. DUT means design under test. That means this design we are testing now. Design under test. With what inputs? So A, B, C in or the inputs. Sum comma carries the output. Very simple description. Okay. So here I just mentioned outputs first, then inputs next, right? So that's why here also I am mentioning outputs first, then inputs. Okay, if you want to avoid the confusion, or else if you are writing some other inputs in the test bench and some other variables in the design, that means both test bench and the design input and outputs are different. Okay, suppose in design A, B, C are the inputs. In test bench, X, Y, Z are the inputs. In design, carry some are the outputs. In test bench, C is the output, S is the output. So then how you can interconnect the both? Just we need to write like this. Whatever the output is there, suppose carry is the design, CY is the name of the test bench. So dot CY carry. And design is a S and test bench is a sum. Just like that we need to connect. And X. So like this, X, Y, sum, C. That means Z. So this is how we connect. Just we need to put dots here. If you write different variable, this is one case. Okay. But if you write the same variables, no need to use all these things. Just you can put same net list. Okay. Same port list. After that, we need to write the test cases. Actually, practically we will tell it as a test cases in UVM verification or in SystemVerilog verification. But here we don't write any test cases. We just give the inputs to the DUT. Okay. So initial, begin. These are the procedural assignment statements. So what are the input and what are the output? Suppose A is equal to 0, B equal to 0, C equal to 0, 0, 0, 0. We need to follow a lot of techniques here, but one by one we will discuss clearly. So 0, 0, 0, 0, 1, 0. We can write the loops instead of this, or by using the always block we can simply write, but just I am showing here 110 111. So all the values we have given here. Okay, so end. Simple, very simple. And we need to display the statement here. Okay, so to display the statement in C language we use a printf. Printf scanf is used to scan the data whatever assigned previously. So after whatever it scan the data, then printf just display the statement. Okay, so in Verilog HDL we use system task, or else we call it as a simulator directives. Okay, so system tasks like dollar display, dollar monitor, dollar strobe, and dollar write. There are different ways, different simulator directives. So one by one you will get understand the difference. Okay, majorly we use dollar monitor. Dollar display also we can use, but we need to use multiple statements if you use dollar display. So here A is equal to percentile B. B means what? It's a format specifier. Okay, in C language, we have the format specifiers, right? Can you tell me what are the format specifiers out there in C language?
Integer, float, double.
Format specifier.
Percentile F, percentile F,
Okay.
percentile D, percentile I. Percentile C also, character.
Okay. Percentile B. Percentile B in the sense binary here. Percentile D decimal. Percentile H hexadecimal. Percentile O octal. Percentile G. G is for? Can anyone tell? G, H.
H
Not
is for
H, M.
hexadecimal.
M, M. Percentile G. That means in C language we have a decimal values, right? Point, 0 point something, 1.1, like some point values. We call it as a float. But in Verilog HDL, we call those as a real values. Real. Okay. So to represent the real values, we use percentile G. Okay. And to represent a hierarchy, suppose multiplexers are there, hierarchical multiplexers are there, that means it will be connected one to one block to another block, connections will be there. So to display that hierarchy like a tree model, we use a M. Okay, so like that we have different format specifiers here. This is how we write the dollar monitor. Okay, now we can do the simulation. Select any tool, click on run. So it will display at the output side. See here. What is the output? Just for more clarity, I'm just writing some lines here. So click on run. Oh, okay. A equal to 1, B equal to 1, C equal to 1. So sum equal to 1, carry equal to 1. Okay, but remaining all didn't displayed. Why it is? Only last one, last scenario displayed.
Timing units not specified, ma'am.
Timing units we need to specify. Okay. So what is the issue we will get if you don't mention any time?
We just
Since there is
get
no
the
delay, we
last
cannot
value
get the
which
data.
execute.
Yeah. Okay. Just wait. Yeah. Please tell, Laharia.
Yes, ma'am. Since we didn't have any delay, so it is not showing the other values.
Okay. So delays must be there with but one by one. Okay. So first one is displaying at 0 simulation time. Second one can display at 2 simulation time or 5 simulation time or 10 simulation time. So third one after some delay. Fourth one after some delay. So that one by one will be displayed. Okay. If I mention all like this, so all are executing, but at the same time all are executing. So whatever the last one is there, that last one is printing here, but all are executing, but we are not able to see all those because one by one executing at the same time. Okay, so that's why delays should be.
Yeah, Prashanti. And where is the functionality like addition, sum and carry? We didn't mention any, we didn't mention any output performance, right? Like XOR operation and AND operation. So from where it is taking and calculating?
See, that's what we did the interfacing here. Adder DUT. These input connections we are connecting to the design here. That means these inputs, whatever the inputs are there, these are connecting with the design here. So automatically do the functionality and we will just get the result only. What is the input? What is the output?
How it is connecting from the Verilog to test bench? Can you explain that?
What?
Yeah, how it is taking that module adder in this text bench? How it is interconnecting with these two?
This is what we call as a interconnection interface. Okay, adder is the name of the design here. Suppose in place of adder I'm writing some other name. Okay, some other full adder name I'm writing. Okay, so this adder name doesn't connect with this test bench. Why? Because this test bench is connecting with some other full adder. Okay, so just run and check now what will be the output. You will be getting the error.
Okay, if we are taking that module name under the test, so it is calling that Verilog code, right? Am I right?
Sorry, it's called Verilog code.
Yeah, it is taking that Verilog code functionality when we call that adder module adder.
Okay.
Yeah,
Here adder module is there. So this design module we are connecting with this test bench. So how it is connecting in the sense here is the interface. Just one line. In Verilog HDL we just write in one line, but in SystemVerilog it is a very complex thing. Okay, so this is how we connect the simply in one line.
Yeah, DUT is compulsory,
yeah, compulsory. If you don't mention the DUT, it doesn't connect to the design with the test bench. Interfacing doesn't happen. Okay.
Yeah.
Here, what is the error it is getting? Here you will find the error. Test bench 8th line. Design unit full adder instantiated in work. TB not found in such libraries. It is not found. Okay.
Yes. Got it.
Suppose in the design I am writing the full adder. Here in the design I am writing a full adder. So both will connect now. See, both are connected. And also I have given the test simulation here. I mean the delays here #2, #2, #5. So delays are given. So that's why it is printing the all cases. Okay. Did you got the idea now?
Yes, I got.
Suppose here there are multiple designs. Same full adder I have written some other full adder. Suppose module adder. Same I am considering. Input and outputs. Another style. Suppose data flow modeling I am writing. Data flow modeling in the sense assign sum is equal to A XOR B XOR C input. Assign carry is equal to A into B plus B into C. Whether this end symbol or dot we will check. And C, just writing expressions. Data flow modeling means just writing the expression. Like this we can write, or another simple way is there. Assign within a single line we can write assign carry comma sum is equal to A plus B plus C. How many of you know about concatenation operator? Just a single line is enough. No need to write these also. We can write these or within single line. Okay. So end module. End module. Okay, this one is for adder. I want to do the simulation of this adder. Okay, then what we can do, just simply remove full adder, full, and just kept in adder. Okay, these values
It will throw error, Prashanti. There in the assign statement, C only you have written. C in, right?
seen. So now this adder will be pointed to this module, not full adder module. Okay, so both the adder here and the adder module both are connected. Okay, just do run and we'll check. See here, adder and that adder both are connected, and also we are getting output only for this. Okay, and next thing is A equal to 0, B equal to 0, C equal to 0, sum equal to 0, carry equal to 0. A equal to 0, B equal to
Prashanti,
0.
if I write that design under test first, if I take the full adder, it will is it going to display two outputs? One more statement under 8th line, the same with full adder.
8th line.
Here, test bench. Yeah. If I take full adder, the one more line with the full adder.
Okay.
Will it display two? I mean, that adder also.
Okay. Two DUTs you want to consider.
Yeah.
Okay. One is adder, one is a full adder. Yeah, it will do. It will display. For in project level, we need to do same, because in project level we will connect a lot of blocks in one test bench, right? So there we need to connect blocks in one top level connection in the same way. DUT declaration, and here identifier is getting wrong. Okay, if so in that case, these two are not hierarchical connection. Okay, so if both the two are hierarchical connection, then we can display. Wait, I will show you the example. Suppose ripple carry adder is there. How we can design the ripple carry adder? Actually, before I thought in the project level, we will have some blocks. Suppose block 1, block 2, block 3, block 4. These 4 blocks are 4 different modules. Okay, so connection between all blocks will be connected in top level block. So this module DUT, this module DUT, this module DUT, all will be connected particularly in the top level. But test bench will be written only for this top level. Okay, we cannot write the test bench for all blocks. We can write it in an individual test benches, not in a same test bench. We cannot mention all DUTs in the same test bench. Okay. Did you got the point now? So
that means for every code we need to write the different DUTs.
Not every that means every design you need to write every different test benches. Did you understood?
Yes, but a bit confused.
No need to confuse. Yeah, just tell me where you got the confusion.
Yeah, just now the previous one you called the TDUTs, but it is to throw the error.
Here in the test bench we cannot call 2 DUTs. If you want to take a 2 DUTs, then you can write the 2 test benches here.
Okay, complete.
So one is for adder, one is a full adder. So this is how we can write. Or else top level we need to connect. TB. Okay, both test bench names are same. So here I am considering one is TB, one is TB1. So okay, see.
Here where you are running, Prashanti, I'm not able to see where you are running.
Here run
Okay,
option.
yeah. Okay.
Okay, see. Another thing is here both are running parallelly. Okay, when both are running parallelly, here we are writing the test cases, test scenarios within the all initial block. Okay, so initial block is the procedural assignment statement we call in a Verilog. It's a very detailed subject. So once we involve into the subject, there you will understand what is initial block and what are the rules we need to follow and what is meant by always block. So here both initial blocks will run parallelly. Whatever the number of initial blocks you are putting in one module, even it's a 10 number of initial blocks or 20 number of initial blocks, according to the delays, all initial blocks will run parallelly. Okay, so that's why same at the same time initial 1 and initial 2 both are running parallelly. Okay, and the delays will be calculated accordingly. So if you want to write the delays, suppose here #2, #5, those all mentioned here. So, but here the delays are not getting. Okay, so you need to put $time here. $time is the system task so that it will print the delays. $time. Okay. So both are executing parallelly. At 0 simulation time, in the first initial block, A equal to 0, B equal to 0, C equal to 0. Parallelly at second simulation time, A equal to 0, B equal to 1, C equal to 1. Two initial blocks. And then next at fourth simulation time, 6th, 8th, next 13th. From here I kept 5. Next 18.
No, actually, if one by one is not, it is not taking some.
Why? Because these are parallel execution. All initial blocks will execute parallelly.
So if we want to print separately, if we want to execute separately, I mean one after another, what to do?
Then we need to write separate blocks. Actually, these two are separate blocks. We never put like this. These are not hierarchically connected. If you connect hierarchically, suppose ripple carry adder is there. Okay, ripple carry adder in the sense it's a hierarchical connection. That means
one after another, right?
yes. So first there will be one full adder, second full adder, third full adder, and fourth full adder. So A, B are the inputs, C is the output, and carry is the one of the, C is the one of the input. And here carry sum, next A0, A1, B1, A2, B2, carry, sum, A3, B3, sum, carry, final carry. Okay, that means by using one full adder, we are connecting multiple full adders here. Okay, then how we can write the program? We just design one full adder first. Okay, by using this full adder, we will take the copies. Okay, same design of full adder, we take copy, second copy, third copy, fourth copy. After taking copies, we will make the connections between each. Okay, so this is how hierarchical connection. Now if you write the program for full adder, that means test bench, then it will generate for test bench. If you write for ripple carry adder, it will generate for ripple carry adder. That also you need to write separately, not in the same block. If you write in the same block, it will provide the parallel output because the flow is parallel execution. Okay, so how the programming style in the sense, see here. Left side, first 14th line. If you observe the 14th line, module, name of the module, full adder, FA. So sum carry is the output, ABC or the input ABC, output carry. Okay, and here output is declared as a range data type. Why? Because we are using the always block. Always block means a behavioral modeling. Just put that thing aside. So carry comma sum is equal to A plus B plus C. So this is what full adder, one full adder we just created a module. Okay. So in the structural modeling, this is what we call as a structural modeling. mostly ripple carry adders, hierarchical multiplexers, hierarchical demultiplexers, or encoder, hierarchical encoders. All these things we will write using the structural modeling only. Okay, so by using this full adder, we are making a 4 instances of the full adders. That means 4 copies of same full adder. Okay, so how we are making the copies? If you see here, 8th line, remaining first till 7th line, just 4-bit full adder top level declaration, some carry AB. So here 3 down to 0. 3 down to 0 means a vector format, because here A0, B0, A1, B1, A2, B2, A3, B3. So that's why we took the size, vector format. 1 bit means scalar format. Okay, so sum also 3 down to 0. That means 4 bit. 4 sum, S0, S1, S2, S3. Next output is carry. Next W. W in the sense wire connections, because here what are the wire connections? This one, C0 is a wire connection from here, C1 is a second wire, C2 is a second wire. Okay, so 3 wire connections are there. So 3 down to 0. Last one also it considered as a wire. So 3 down to 0, W. Next, what is the module name here for full adder? FA. Okay, so FA, name of the FA is FA1, created 1 full adder, FA, FA2, second full adder, FA3, third full adder, FA4, 4 full adder. That means 4 copies, because 4-bit full adder. Okay, 4-bit triple carry adder. Next, we need to make the connections here. We just declared the instances here, just need to make the connections. So sum of 0. First output, sum of 0 is the first output. W of 0. W of 0 means first carry. Okay. And then carry output. And then A0, B0, input. C input is a 1. Either 1 or 0. If you want to write a subtractor, last time in combinational circuits we discussed, right? Adder and subtractor in a same. So that is a mode. If you want to put mode signal, you can put, or else 0. Okay. And next, sum1, W1 is the next carry, A1, B1, W0. That means this W0, this one, and this will be the input and this will be the output. Okay, so W1, W0. So W1, W0. Next, W2, W1. Next, carry, W2. Okay, so this is how we make the just 2 down to 0 enough here. Yeah. So top level we will connect a ripple carry adder. Okay, so we'll do the synthesis of this. Then you will understand how the connections are happened here. Go to quarters prime in the same Verilog module. I'm just copying this. And did you understood the coding style? Others, Suma, remaining how we have written the coding?
Yes, ma'am.
Aditi, Madhav, Ritesh, Abhay. Okay, so compilation is successful. Go to netlist viewer, RTL viewer. Okay, so this is how the ripple carry adder will be generated. Okay, so inside this you can observe the program here. Okay, here inside the block I just took sum equal to carry plus, sum carry comma sum equal to A plus B plus C. Just a simple diagram, simple logic. Okay, if you write a gate level, before we have seen gate level program here, right? Like this. If you take this program, then it will generate a inside it will generate the same program. I just want to show that also. In place of a single line, I'm considering this one. Okay, so the name is FA here. Okay, remaining all are same. Carry comma sum. Sum comma carry ABC. Okay, same ports I want to consider. Carry comma sum comma ABC, and here also A B C, and here also A B C, A B B C, C A, and carry correct. Okay, so here I'm considering gate level circuit diagram before data flow model. Data flow model means it's just like a behavioral kind of logic, just that is good for logical implementation. Okay, but if you want to check a detailed structure, then gate level is good. Okay, if you write a behavioral modeling, you won't get a detailed gate level structure. You will be getting like this only, just a adder, and here adder one is for sum, one is for carry. But if you want to check detailed structure, then this programming style we need to consider. Okay, just save and run. Actually, we need to discuss these things very slowly. If we discuss in the first session itself, it gives a lot of confusion for you. Okay, today I just want to discuss very basic things, but I need to show for your doubts. I need to explain, right? So that's why I just showing. So 100% compilation is successful. Okay, so go to netlist viewer and RTL viewer. So this is how a 4-bit triple carry adder will be designed. Okay, so netlist. Inside this you can observe. Inside a full adder, how the circuit diagram is there. Okay, inside the full adder, how the circuit diagram. So like this. And here also. Okay, so this is how we will design the 4-bit ripple carry adder. Same hierarchical multiplexers also we write in the same way. Okay, so if you want to do the simulation of this design, how we do the simulation? For which module we will write the test bench now? Can you tell me, Sumulata, for which module we need to write the test bench?
FA?
For FA?
Yeah.
If you write FA, which signals will be tested?
It is a copy of 4 copies, but I'm not sure. U1, U2, U3, A, B, C.
FA, we didn't make any copies.
Okay.
Do we have any copies in FA?
No.
Then what we will get the output if we write for FA?
But
To verify this ripple carry adder, for which module we need to write the test bench now? Other
FA only, but some carry A, B, C are the inputs. For the vector inputs, I'm not sure. I mean, maybe we need to give the inputs like bits, I mean decimal bits. I'm not sure.
So you want to write the test bench for FA, right?
Yes, I
Okay.
think.
What about remaining? Any answers from your side? How can I write test bench and how can I check the output?
I think we need to have 4 test benches, and that 4 test benches we need to call in one test bench, that is top level test bench.
Okay.
I think in that way we can do.
Okay. Fine. Remaining, any answers? Can't we write only
Ma'am,
yeah.
we can write a single test bench for the whole ripple carry module, in which we have called full ladders 4 times. For that, we can write test bench with the inputs A, B, and outputs
What
as
is your name,
some
Rahman?
command carry. Yes, ma'am.
Rahman, Madhumita, and who is she? I didn't remember. Vishnu. I don't consider your 3 answers. Okay. Other than these, better anyone can answer. Any other answers? Because you already learned Verilog, you already know Verilog, right? That's why. What
Yes,
about Ritesh? Ritesh, Abhay, Aditi, Lahari. How can we write the test bench for this? If you write the test bench for full adder 1 for only this module, only one full adder module will be verified, or 4 full adder modules will be verified. That means we will get the output at this point, and here, and here. This carry sum, and this carry, and this sum. Okay, but we don't get the output at the top ports. These are the main ports, right? At the first starting of the session, I told you what are the main ports and what are the internal signals. For this ripple carry adder, here the sum and carry, these 2 are output ports, and remaining these 2 AB are the input ports, main ports. Remaining whatever the signals are there inside these are all wire connections only, not main input and output ports, right? These are all just input internal connections, wire connections, one gate to another gate connections. Okay, so in that case, for which ports we need to apply the inputs? We need to apply the inputs for these main input ports, and also we need to check output for these 2 only. Okay, that means we need to write the test bench for these inputs and need to check the output for these. That means total overall ripple carry adder at the top level, we need to write the test bench. Okay, not for the internal signals. If you write a test bench for FA, it will just check only for this circuit, and we will get output for here and at this point of time, not at main output ports. Did you got the point, everyone?
Yes, ma'am.
yes.
So that means here 4 blocks are connected. To these 4 blocks, the top level is the main block. So these are the input ports and output ports. Remaining internal connections are nothing but wires. Okay, so we need to apply the inputs to main input ports and to output. We need to check. Okay, so for that reason, we are writing the test bench here. Suppose without writing the main test bench of ripple carry adder, if you have a doubt, suppose whether this full adder is working properly or not, if you want to check whether this full adder is working properly or not, you can check. Okay, so first, how you can check only for full adder? Just need to write the DUT name as a FA. Okay, that means this 7th line FA is connected to this module FA. Okay, as of now, I am checking only for FA, not for ripple carry adder, not for main top level module. I'm just checking for only single full adder, because if that full adder works, automatically the top level ripple carry adder will work. Okay, always we need to do the verification from lower level. Okay, so that's why we need to check full adder first and then top level. So full adder test bench is correct. AB or the input, sum is the output, carry is the output, but small change will be there. What is that? What is that small change? Observe the input and outputs here and here also.
The vector formats of input.
Vectors. Okay, so here we need to change the values here, or else I'm just copying these and taking another module and just comment this. Okay. So now I'm just removing the vectors here, and in place of A, B, just give the values as a 0, 1, and C also. C equal to 1 and 1, 0, C equal to 0, B, A equal to 1, B equal to 1, C equal to 1. Okay, now check what is the sum and carry. Okay, only for full adder. Run. So simulation time is 5. Undeclared identifier C. Okay, here C need to declare. We got the output. Did you observe? C not declared. So I have declared the C. Okay. So what is the output now? Initially, if you observe, sum equal to X, carry equal to X, A equal to X, B equal to X. That means at 0 simulation time, I didn't given any input here. Okay. I have started at 5 simulation time. From 5 simulation time, A equal to 0, B equal to 1, C equal to 1. That is what the inputs are mentioned here. So A equal to 0, B is equal to 1. And also in dollar monitor, I didn't return C. So that's why B after C, percentage B, comma C. Mention C also, so that it will display properly. A equal to 0, B equal to 1, C equal to 1. So 1 plus 1, 2. So sum equal to 0, carry equal to 1. Correct. A equal to 1, B equal to 0, C equal to 0. Next one. So sum equal to 1, carry equal to 0. Correct. Next one, A equal to 1, B equal to 1, C equal to 1. So sum equal to 1, carry equal to 1. So only three scenarios I have taken here. So for 3 scenarios, we got the output. Okay, we just check with the full adder module only, not for ripple carry adder. So if you want to check with the ripple carry adder, instead of this FA, we need to mention, I'm just removing this. Did you understood everyone? Do you have any doubts here?
And can you explain that concatenation statement?
Concatenation. Okay. So here, what is meant by concatenation? Can anyone tell what is meant by concatenation operator? Actually, in the next session, we will get the operators, but no problem. I can explain. So concatenation operator means combining. Suppose A equal to 2, 0, B equal to 1, 0, 1, 0, 2, C equal to 1, 1. Okay, so if we write a concatenation, that means A comma B comma C. That means all the three values will be combined. That means A equal to 2, 0. 2, 0 will be combined. B equal to 1, 0, 1, 0, 2. C means 1, 1. So like this, all the values will be combined. That's what we call as a concatenation operator. Okay. So here carry comma sum. That means carry and sum values both are combined. For what? A plus B plus C. Suppose A equal to 0, B equal to 0, C equal to 0. Sum carry 0, 0. A equal to 0, B equal to 1, C equal to 0. So sum is 1, carry is 0. So here carry will be assigned with a 0, sum will be assigned with a 1. Okay. Suppose 1, 1, 1, triple 1. Triple 1 means output is double 1. So this 1 will be assigned to carry, this 1 will be assigned to sum. As we mentioned here, A, B, C. Like that, this one carry, this one sum. Like that, 0, double 1. 0 double 1 means how much? 1, 0. So 1 will be carry, 0 will be sum. Because 1 bit only, right? Both sum and carry are single bit. So 1 will be assigned to carry, 0 will be assigned to sum. Just a single statement, we will get the full adder logic. So these kind of things are helpful in the projects, because there we design complex designs where we combine lot of blocks at a single top level, right? So these type of things will be helpful there.
Yeah, this is for only for single bit or multi-bit
Single.
also, is it only for single bit, right? Yeah.
Yeah. Even for multiple bit also we can do. For carry we need to declare, and for sum we need to declare. So based on that, suppose carry 2, sum 5. So based on that it will divide. Maybe you can try once. Okay. So next, any other doubts? Others? Till here, any doubts? Ritesh, any doubts? Madhav, Lahari, Ahmad, Abhay and Aditi. Are you there?
No doubts, ma'am.
What about Ritesh? Aditi? Remaining? Aditi and Abhay. Tell yes or no. Ahmad? Are you there in the session? Hello? Okay, I will talk with you later. So here I am just removing the test bench, this one. And whatever at starting we mentioned, just a vector is different. Remaining all are same, just vector is different. Here instead of single bit we are mentioning 4-bit size. Okay, and instead of FA we need to mention 4-bit adder, the name of the design, whatever the name of the design, same. DUT sum carry AB. Okay, do run. So A equal to 5, that 5 will be divided into 4-bit, B equal to 4, it will be converted into the binary. So A equal to 10, B equal to 8. C. A equal to something, B equal to. And what is sum? Carry. A equal to 1010, B equal to 1000. What is sum and carry? A equal to all ones, B equal to 0010. Then what is the sum and carry? Okay, so clear everyone till here?
Yes, present.
Any doubts?
Ma'am, in the test bench, while declaring the module, can we write it DUT with other name like DUT1 or DUT2?
Yeah, we can write any name. Suppose here full adder, 4-bit adder is there. You can mention as a ADDR. No need to mention only DUT. It's a user defined. You want to mention like DUT1, DUT2, like that.
Yes, ma'am. Not only DUT1 but other name also. So
Yeah,
can we define then different modules with different names?
Defining different modules with the different names means?
Like for now we have defined for a 4-bit adder, right? Uh, in the next line, can we define for full adder with a different DUT, like as a FA?
Yeah, that's what we cannot declare multiple DUTs in single test bench because the variables will not be same, right? Because this DUT is a single bit variable, ABC or single bit, but here these are vector, and also C is not there here, but here we need to mention C, so it will be wrong.
Okay.
We
Okay,
need to
ma'am.
write different test bench for different designs.
Okay, ma'am. Got it.
Any doubts, others? Okay, today I will share you assignment 1. I think everyone, okay. Actually, today I thought of discussing 4 levels of abstracting. That means how to design behavioral, data flow, gate level, and switch level. But we didn't discuss that. Okay, then no problem. Tomorrow I will share the assignment. Okay. So once these are completed, then you can start working with that assignment. Meanwhile, everyone submit assignment 1 and 2 from digital logic design. Okay. And also another thing, I shared the materials yesterday, right, through Outlook.